And welcome to chapter 10, where we're going to be focusing on the unit of the mole. The mole is a special unit that we use in chemistry that combines what we know about weights and measures with what we've learned and discovered about how small the atom is. And so we'll be diving into what the mole really means kind of by the end of our topic here. But for now, we're going to get started with a concept of how to tell how much a particular atom or molecule might weigh, or how much mass that atom or molecule may have. We're starting our topic with formula mass, and an important thing to know about formula mass is that it measures a weight of an atom. Now remember that weight and mass are not exactly the same thing in physics, but as long as you're on Earth, we made an exception and we said we can discuss weight and mass as if they are the same thing. So in chemistry on Earth, the mass of an object is going to be measured in grams. And that's the kind of thing that if I were you, I would write down in my notes right now to make sure it's something that students forget or are unsure of on the test. That weight is measured as mass and mass is measured in grams. So weight, mass, and grams are all going to be kind of interchangeable terms as we're talking in this chapter. So let's look and remember what a single molecule weighs in AMU. So what you might remember is that an AMU is an atomic mass unit. And this was something that we learned last semester where we said that carbon 12 weighs exactly 12 AMU. And we did some math to figure out how to find the weighted average of an element. Now, instead of looking at just a single element or atom, we're going to be combining that information to look at how much does a whole compound weigh or a whole molecule weigh. So to revisit what the average atomic mass is, it is the average according to percent abundance. So an individual carbon atom may weigh 12 or 14, but when we account for the percentage, then we can determine the average atomic mass. And hopefully you can recall that the average atomic mass is listed in the periodic table just or below the element's name. We're going to take a minute to just kind of zoom in on the periodic table so that we can get a feel for where we would find the average atomic mass. So we'll start by looking over here in the P block. And if we look at oxygen, what we find in the box with oxygen is in the upper left-hand corner, there is a number 8. And that 8 represents the atomic number or the number of protons that are in oxygen. Underneath the symbol O, we find the term oxygen to tell us its name. And beneath that is a number 15.999. And that indicates the average atomic mass of oxygen according to its percent abundance when you consider the abundance of all of the different isotopes of oxygen present in the universe. The average of their mass is 15.999 atomic mass units, or AMU. Now is we are going to determine the formula mass for H2O. And so the first thing we need to do is locate hydrogen and oxygen on the periodic table. So I challenge you right now to get out your periodic table and make sure that you can find hydrogen and oxygen. So what we're going to do is we're going to start by identifying how many and of which elements are in water. So I start out by identifying that according to H2O, that tells me that I have 2 hydrogens and 1 oxygen. 2 hydrogens and 1 oxygen are present. The next thing I'm going to do is look up each of hydrogen and oxygen's average atomic mass. I'm going to use a different periodic table for a moment that's a little easier to see. So we're going to start by looking over here at hydrogen. And I can see that hydrogen's average atomic mass is 1.008. And we're going to always round off to 2 decimal places. So in this case, the 8 is my deciding decimal place, and that tells me that the 0 in front of it becomes a 1. So hydrogen's average atomic mass is 1.01. So where I have my hydrogens, I'm going to write times the average atomic mass of hydrogen, which we just checked and found, is 1.01. Now I'm going to do the exact same thing, but this time with oxygen. Oxygen's average atomic mass, as written on the periodic table, is 15.999. The third 9, this one's tricky. The third 9 rounds us up all the way to 16.00. So oxygen's average atomic mass is 16.00, so I'm going to put that with oxygen times 16.00. So altogether, here's what I'm looking at. The formula mass for water is going to be 2 times 1.01 and 1 times 16.00. So I'm going to do my subtotals here. This is 2.02 due to hydrogen and 16.00 due to oxygen. Now I'm going to add those up and I get 18.02. And because I'm finding formula mass, I know that my unit for this is AMU, or atomic mass unit. So I have my answer of 18.02 AMU, and that is the answer. And just as a note to yourself, the first question on the test will be just like this, finding the formula unit from the average atomic mass on the periodic table. So we're going to try 2 more practices together. We're looking for what the mass is of a glucose molecule. Glucose's formula is listed here, and it starts out with carbon. So we're going to look over at carbon. Carbon's average atomic mass is 12.01, and you can tell from the formula of glucose that there are 6 of those. 6 times 12.01, enter that into your calculator, and you would get 72.06 AMU. Next, we look up hydrogen. And in our formula, we see that there are 12 hydrogens, and we look them up on the periodic table, as we did in the previous problem, and hydrogen is 1.01. I get 12 times 1.01 to give me 12.12 AMU. And last but not least, we look up oxygen. We already did that one too. We come over here to find oxygen, and remember, oxygen with 15.999 becomes 16.00. 6 of those times 16.00, 96 AMU. And now I will add them up to end up with 180.18 AMU. I hope it went well. What we're going to be doing now is we're going to give you a chance to practice carbon dioxide and, do you remember the name of this? Ammonium carbonate. We're going to give you a chance, you can't forget your naming, we're going to give you a chance to try and work out these ones. So let's start out by all working out carbon dioxide together. Make sure you have your periodic tables with you, because I'm going to expect that you are looking up as we go. Dioxide has 1 carbon, and each carbon weighs 12.01. Carbon dioxide has 2 oxygens. Each weighs 16.00 or 32.00. And we add those numbers together to get 44.01, and our units, of course, are AMU. Trying again with ammonium carbonate. The tricky part to this one is the subscript. This 2 applies to nitrogen and to hydrogen. So we're going to have to distribute or multiply through. So for this problem, we end up with nitrogen, hydrogen, carbon, and oxygen. We have, as we distribute, 2 nitrogens, 8 hydrogens because we multiply the 2 times the 4 to give us 8, 1 carbon, and 3 oxygens. When we look these up on our periodic table, nitrogen is 14.01, hydrogen 1.01, carbon 12.01, and oxygen, of course, is 16.00. Maybe this is coming to a point in your life where you're ready for a calculator, in which case we can multiply 2 times 14.01. I think you can still do that one, 28.02. 8 times 1.01 is 8.08. 12.01 times 1, 12.01. And last but not least, 3 times 16, 48. Now the calculator comes in handy. We can add these all up together. 28.02 plus 8.08 plus 12.01 plus 48 gives me 96.11. And do you remember the units? If we're doing formula mass, our units are always AMU. Very nice. Box your answer. Always box your answer. Guys, so we got through our formula mass. Now, the problem with formula mass is that it is impractical. Unfortunately, even though we know an AMU and we can apply this atomic mass unit to multiple different elements on the periodic table, what they don't help us do is measure on a scale. A scale measures in grams or ounces or pounds, but never in AMU. AMU is not an actual unit that can be used in a weights and measure kind of environment. So although it's a good scale for comparison, which one's bigger or which one's smaller, carbon has 12, oxygen 16, so oxygen is bigger, it doesn't tell us how to go to an actual scale and get a certain amount of oxygen or carbon. To answer that problem, Amadeo Avogadro came up with the concept of a number where when you collected that number of atoms, it would convert AMUs into grams. Now, I, for one, am very happy to not need to do the math for this conversion. Avogadro derived this math for us. Thank you, Avogadro. All you need to do is say thank you to him, and now we can use his number to make our values much more meaningful. So Amadeo Avogadro went to work and calculated the number of carbon atoms necessary to make 12.01 grams of carbon to be 6.022 times 10 to the 23rd. This number has become known as the mole. 6.022 times 10 to the 23rd atoms or molecules makes up 1 mole of any substance. So if I wanted to have 1 mole of pens, I would need to get 6.022 times 10 to the 23rd pens and put them all together in a container. That's a lot of pens. It's too many pens. But when you're talking about atoms or molecules, we're talking about very, very small items. And so you need a lot of them in order to make an appreciable or measurable amount. So we have 6.022 times 10 to the 23rd atoms or molecules in a single mole. This number is incredibly helpful, and we should all be grateful to Avogadro for coming up with this number. So now we know that the average atomic mass also represents how many grams that element would weigh if you had 1 mole or 6.022 times 10 to the 23rd of them. And we say now that the units, instead of being AMU, are going to be measured in grams per mole. So the mole word that reflects a number. So the mole is 6.022 times 10 to the 23rd atoms or molecules. A dozen is a word that reflects a number. You know that number, it's 12. If I said, oh, I have a dozen eggs for you, you would know exactly how many eggs I had for you. A baker's dozen is 13. In the week of the inauguration and in the week of political speeches, 4 score and 7 years ago would be 4 times 20 and 7, 87 years ago, 4 score. You know who said that? Abraham Lincoln. Thank you. Okay, and a gross is another word that means a number, which is 144. So we have many words that reflect a number, and the mole is just like that. So the mole, 1 mole, is equal to 6.022 times 10 to the 23rd molecules. That is a relationship that you should memorize, or at the very least, distance learning, have written down on a piece of paper that you will be using during the test so that you have that specific information with you. What we're going to do now is reflect on how amazing this conversion factor was that Amadeo Avogadro gave us. So if you will recall, a few slides ago, we looked at the formula mass for water. So I want you to get that bit of notes out of how we found the formula mass for water. Now we're going to define the molar mass for water. We call it the molar mass because we're using 1 mole of substance. We're using that word that means a number, the mole. And so we're going to call it the molar mass as opposed to the formula mass. Formula mass is measured in AMU. 1 mole of water has 2 times 1.01 grams per mole of hydrogen and 1 times 16.00 grams per mole of oxygen. We add it together and we get 18.02 grams per mole. Does that feel familiar? A moment ago, we got the formula mass to be 18.02 AMU. So in essence, what Avogadro has done for us is made a 1-to-1 conversion factor so that any value of formula mass is exactly equal to the value of molar mass. All we need to do is change the units. So real quickly, what are the units for formula mass? They are AMU, or atomic mass units. And what are the units for molar mass? Well, they are grams per mole. Let's think about that term, grams per mole. Conversion factors that you may have used in your life before. The first one is miles per hour. I don't know if you've ever been sitting in the car and a sign comes by and tells you how much farther you have to go, and you realize that you have to go 120 more miles, and you can quickly determine that that means, since you're going 60 miles per hour, that you won't be home for 2 more hours, 2 more hours in the car. Another thing you can figure out is if you were to know that you were making $100,000 per year, you could very easily figure out that in 4 years, you would have made $400,000. These are simple math problems. We are doing more simple math problems, but we are using a different value. Instead of miles per hour or dollars per year, we're using grams per mole. So if I know that something is 40 grams per mole, if I have 2 moles of that something, I know that I need 80 grams. So grams per mole tells us how many grams in each mole we have available for us. And this allows us to weigh and measure our amount of moles by measuring our mass. So this new kind of term with grams per mole, we call the molar mass. And the molar mass is going to be the foundation of this entire chapter. Almost every problem that you will need to solve in chapter 10, 12, and 14, for that matter, you will need to solve a molar mass first as the very first thing you do. So learning to solve molar mass is really foundational, fundamental to your success in this semester of chemistry. So we're going to take a second and calculate the molar mass for two more compounds, SO2 and NH43PO4, sulfur dioxide and ammonium phosphate, if you remember your naming, which I hope you do, because that test was yesterday. So we're going to go over calculation of the molar mass of those two compounds. So what I want you to do is start by calculating SO2 on your own. Quickly and easily, you can deduce that you need 1 sulfur and 2 oxygens in order to do this problem. So now I want you to go look up and record the molar mass for sulfur. 32.066 rounds to 32.07 for sulfur. And for oxygen, once again, 15.999 becomes 16.00. We do our preliminary multiplication and we get 32.07 and 32.00. Now we just add those together and we get 64.07. And fundamentally important to what we're doing right now is the unit of this answer. Remember, we're finding molar mass, so our unit is grams per mole. Grams per mole. A funny thing about the mole is that its abbreviation is just MOL. All we save you is an E. Not a super useful abbreviation, but that's all we've got. Okay, M is for mass or meter, MO is an element, molybdenum, and so MOL is kind of the shortest we can handle. So the abbreviation for mole is MOL. Now what I'd like you to do is try the next one, NH43PO4 ammonium phosphate. So we start by identifying the 4 elements that are in this compound. I have nitrogen. How many nitrogens do you see that I have? 3 nitrogens. How many hydrogens do I have? Remember to distribute. 3 times 4 is 12. Good job. Phosphorus, there's just 1 of those. And oxygen has 4. Once I have my numbers down, I go look up on the periodic table for each of their individual molar masses. Now you don't need to memorize any of the molar masses. You're obviously always going to have a periodic table, but sad to say that as you get nerdier and nerdier, as you do more and more of these, you may accidentally start to memorize them. So let's start. You can use a calculator or not if you need to. 14.01 times 3 is 42.03. 12 times 1.01 is 12.12. 1 times 30.97 is 30.97. And last but not least, 16 times 4 is 64. Take a moment and add those all up. I got 149.12. And my units for that are grams per mole. Is that what you got too? So with the success of finding the molar mass of ammonium phosphate, you now know how to find the molar mass, which is the foundation for all of chapters 10, 12, and 14 for sure, probably sprinkled in all the other chapters as well. Your chemistry foundation is getting really strong. When I see you in class, we will practice some of these formula mass and molar masses together to make sure that you really have them. But if you have any questions, make sure you write them down and we'll go over them in class when I see you. All right, guys, have a great night. Talk to you soon.